should.
Checked.
Yeah, did you get the fire alarm recorded?
Did not. So we looked at some examples yesterday. Here's kind of a classic example.
Yeah. That,
Okay, so this one illustrates the benefits of implicit differentiation, right? So what's the difference? Implicit differentiation, first of all, we're able to deal with problems that we otherwise couldn't do. There's no way we could solve this thing for y, right? Solving that for y explicitly would be a really bad deal. So if we just apply the chain rule and differentiate implicitly, meaning we're just going to differentiate everything with respect to x, in that process, by the chain rule, any term that has a y in it is going to give rise to a y prime, right? And so when we just collect all those y primes and isolate them, then that algebraically allows us to solve for y prime. Now we might get some horribly ugly answer, but that's all right. What are we using y prime for anyway? Probably just to calculate a derivative somewhere, calculate a slope. So we're just going to be plugging in values of x and y. Now why is it in this case that our answer for y prime includes both x's and y's, which is very different than what we've had in the past? When we have an explicit function of x, then we have y as a function of only x's, and so when we differentiate, we're only getting x's back, right? How come we've got x's and y's here? And why might that be important? Let's go back and look at. Okay, well, so here's an example where maybe you can see, because we've got a graph, this was a circle, right?
oh, because it's not
There's gonna be 2 points.
Okay, there could be multiple places, there could be multiple y values for a given x where we have a tangent line, right? If it's a non-function, like this one is where it violates the vertical line test, we have to specify when x equals 1, there's more than one place on this relation where x equals 1. And so we're going to get different tangent lines depending on which specific point of tangency we're picking. So we have to specify both an x and a y value to pin down the point of tangency. Yes, sir.
So as soon as a y is inserted into the equation, it's no longer a function? Because that means there's multiple y values for a point, and that would no longer make it a function.
Okay, so is that always true? I think that's true, but I guess I wouldn't, I think it is, but I'm not going to say definitively that it is. Yeah. Yep.
So if you have like a circle or even like a parabola or anything like that where you're finding slopes and you're gonna find it at 2 points, aren't they always gonna be opposites of each other since they're like reflections on top of each other? Aren't the slopes always gonna be like
Okay,
opposites?
so the answer is no. It is, the examples we've looked at, they have even symmetry about the x-axis. Yeah. And so in the examples we've looked at, that's true, but it wouldn't have to be that way, right? It wouldn't have to be that these have folding symmetry over the x-axis. So it wouldn't, in general, no, but the ones we looked at, yes. How could we talked about even and odd symmetry before, right? We talked about even and odd symmetry when we're talking about functions of x. We said even symmetry, you remember the test for that, right? This is kind of a little side note here, but it's worth mentioning maybe. So, right. So we said even symmetry, just a quick review. F of negative x equals what? Now, and how do you, I mean, you don't want to try to remember that fact because you'll forget it, but even symmetry means that's going to be folding symmetry about the y-axis, right? That's really all you have to remember. F of x, right? And why is it even? Because if we're talking about a power function, it would be a power function with an even exponent. So we would take the classic example, x squared, if y, or f of x, I should say, if f of x equals x squared, then if I go over positive x or back negative x, don't I end up with the same y value, right? See what I'm saying? We've got that folding symmetry there, okay? Odd symmetry was what? F of negative x equals negative f of x, good. Now, we're talking about even and odd symmetry with respect to x, right? So we're talking about even symmetry about the y-axis. How could I tweak that a little bit and say even symmetry about the x-axis? If it's even symmetry about the y-axis, the function was insensitive to the sign of x, right? That makes sense? Okay. If it's even symmetry about the x-axis, what would be insensitive to? Sign of y, right? So this would be an example where f of negative y would just equal f of y, and that's what we got in each case. Okay. Like for example here, if I plug a negative y in, it's not going to change anything, is it? It's being squared. Okay. So this is one that's, it's going to be even with respect to both axes, isn't it? This has, I mean, it's a circle. It has all symmetry, doesn't it? It has even symmetry, it has odd symmetry, right? See what I'm saying?
Yeah.
Okay. All right. So what about this guy? So now we're moving on to a second derivative. And this is an example we need to look at, because the second derivative complicates things just a bit. So let's start off with here's our implicit equations, not solved for y. If we differentiate implicitly, what are we going to get? 9. Okay, so I'm going to differentiate with respect to x. The first term is just going to give me 9. Second term is going to give me 3 times y prime, good, equals, now the derivative of sine y with respect to x, chain rule, right? Derivative of sine and is cosine y prime, okay? So we could, I mean, we've done problems like this now. We could solve for y prime. If I were just to isolate the y primes, like I could subtract a 3y prime to this side, right? And then what would I be left with? So if I want to solve for y prime, I'm going to get all the y prime terms on one side, and the numerator is just going to be whatever's on the other side, right? So that's a 9. Everybody agree? Okay. What the denominator is what I'm going to be left with when I factor the y prime out and divide the rest away. So I'd have a cosine y minus a 3, right? Okay. That's not my answer. I want y double prime, second derivative. Remember, that's my goofy notation for second derivative, right? So what are my options here? There's no one path, but maybe we can come up with a better path. The second derivative is, how's it related to the first derivative? Derivative of the first derivative. So I could go from here, couldn't I?
Yeah.
I mean, here I've got, this is explicitly solved for the first derivative, so I could just differentiate this with respect to x and get a y double prime, right?
Mhm.
Okay, what else could I do? Okay, I could do with the original one, and I could just continue differentiating implicitly with respect to x a second time. Generally, that's going to be better, because you're not going to have to deal with, this one isn't so bad because I don't have a function on the top. So I could rewrite this as 9 times the quantity cosine y minus 3 to the negative 1. But what if I had x's and y's on the top and the bottom? Then I've got a quotient rule wrapped in there. Quotient rule is, I mean, wouldn't you agree, quotient rule is a little bit messy, right? We prefer to avoid that. So if we were just to go, just continue on from this step here and differentiate implicitly again, derivative of 9 is 0. Here I'm going to get a 3 y double prime, good, equals, now here I've got a product, right?
Yeah.
So I got to do product rule. That's okay though. So I've got cosine y times, okay, good. So the first times the derivative of the second plus the second times the derivative of the first times y prime. Okay. So let's rewrite that then. We've got 3y double prime equals cosine y, y double prime, plus, or minus, let's do. Got a negative there, minus sine y times y prime squared. I've got a y prime times a y prime, right? Okay? So solving for y double prime is no big deal. I'm just gonna subtract that term to that side, and then I'll divide everything by, factor out the y double prime and divide, right? So maybe we'll just show one intervening step there. I could, when I do all that stuff, if I subtract this term to the left, the y double prime term to the left, and factor out a y double prime, everybody agree I'm gonna get that?
Yes.
Okay. And on this side, I've got a minus sine y times y prime squared, so that if I want to solve for y double prime, I'll just divide everything, both sides by that factor. I get y double prime equals negative sine y over 3 minus cosine y times y prime squared, right? Okay, is that a good answer? It's not terrible, but what's a little goofy about that answer?
For y prime.
I got a y prime in my answer for y double prime, right? It'd be nice if we didn't have to do that. If we would really like to be able to just define y double prime in terms of x's and y's, right? So we can just take the coordinates of our point of tangency, for example, and calculate what the second derivative is going to be. Now, we haven't talked about yet what the meaning of the second derivative is, but we will shortly, and it's something we want to know. It gives us some valuable information. It's not slope, it's something different, but it's valuable, okay? So what can we do then?
You could put in what the 9 over cosine.
Right, you see that? I do have a previous step where I solved for y prime. Right? So I could just plug that in instead, and then I end up with y double prime equals negative sine y. And really, it's not a big deal, but I could also just factor a negative out of the top and bottom right there, and call that sine y over cosine y minus 3. Okay, times that squared, right? 9 over cosine y minus 3 squared. And then if I wanted to, I could even clean that up a little bit and say 9 squared is 81, right? So I got an 81 sine y, and what's on the bottom?
Cosine y.
Minus 3 to what power? Yeah, I got 2 of them there and 1 of them there, right? Okay, makes sense. Okay. Let's see. I don't know if we even need to do that one necessarily. I'll tell you what we'll do instead, because that's really similar to one we already did. And I'd rather you just get some practice on it. But what do we mean by a normal line, though? That's the one thing I want to talk about on this one. Tangent to a curve is the line that's parallel to the curve at a given point. We just put a normal line. So we haven't probably talked about it. Normal means perpendicular. Is that what you saying? So so the normal line is going to be the perpendicular to the curve. And when you go on to, the next year, when you're taking calculus classes in college and you do multidimensional calculus and multivariable calculus, and you're doing, instead of just doing 2-dimensional curves, you're doing 3-dimensional surfaces, and you want to find a tangent. Well, we talked a little bit about that at the start of the year. That's going to be like the fall line in your steam or something, right? So that's going to be the one line on the surface that's going to be parallel to the surface, right? And then the normal line is going to be the one line that's going to always be perpendicular to the surface at that point, right? So if you were to focus in and flatten out the surface, it would be the one that's sticking straight out of the surface perpendicularly. Okay, so let's go back to a previous example then. We did this one, right? And we wanted to find the tangent to the curve at that point. So that's where we didn't actually do it. But if we plug in 2 and 1 for x and y, that's going to give us the slope, right? Does that make sense? Okay. If we wanted to find the slope of the line tangent to the curve, then, if we wanted to find the tangent line to the curve, here are my values of x and y, right? And then really all I need to do is find the slope at that point. To do that, I would plug the 2 for x and 1 for y into this, correct? Okay, what's the only difference if I wanted to find the equation of the normal line? Does the point change? No, the point doesn't change. If we've just got a general curve, so there's my xy plane, and here's the function. If we want to calculate a tangent line right there, well, we've got a point of tangency and we've got a slope that we get from the derivative, right? If I want to calculate a normal line, the point of tangency and the point of normalcy are the same, right? So it's going to go perpendicular to the tangent. So the value of x and y are the same. What's the only thing I'd have to change? What would I do to the slope of the tangent line?
Negative reciprocal.
Yeah, just make it the opposite reciprocal. So I would still calculate the tangent to the curve, but once I find the slope of the tangent line, I find the perpendicular slope from that. Flip it and change the sign, right? Okay? And then want to do that one or not?
Sure.
Let's do the last one, and then I'll turn you loose and let you work on this stuff. Okay, so here's our original equation. What if I differentiate implicitly? What am I going to get? So I've got chain rule stuff, right? I'm differentiating with respect to x. So the derivative of e to the hand is e to the hand. So I get e to the 4y times the derivative of 4y with respect to x.
4y prime.
4y, or 4y prime, right?
Yeah.
Yep. Okay. Plus 1 equals 5y prime. Okay. And then if I wanted to calculate y double prime, I could just go through and differentiate again, right? So that would give me the product of these two, right? So I get e to the 4y times the derivative of 4y prime would be 4y double prime, good, plus 4y prime times the derivative of e to the 4y, which we already did. E to the 4y just gave us that whole thing for the derivative, didn't it? Derivative of 1, 0, equals 5y double prime. Okay. So we could maybe keep this term positive and subtract that term to the other side. So I get 5y double prime minus 4 e to the 4y y double prime equals that. So what is that? 16 e to the 4y y prime squared. Factor out a y double prime, divide the rest away, and we get y double prime equals this stuff. That's weird. Right, so that's what's on this side. If I factor the y prime out, I'm going to be left with what did I have to divide both sides by? And then I would just, if I wanna know what y prime is, I just would go back to this step and solve for y prime and plug it in. Okay? Make sense? Okay? Alright, I think, did we ever do, or did we ever finish that? Oh, that one. So what about that one? We kinda gotta know what's going on with this, don't we? We gotta know the rate at which the speed that blood's flowing is changing, right? So S prime. And they give us, remember, R is the radius of the artery. Remember the picture from yesterday? I drew a picture somewhere. Yeah, there's my great picture. So there's our blood vessel. The distance, small r, is going to be some distance from the center of the artery. And this time we're going to dilate the artery, so the capital R radius is going to change. But we want to know for a fixed radius from the center, how fast is the speed of the blood changing, right? Okay, so what are we going to do? What am I trying to find? S prime meaning dsdt, right?
Yeah.
Okay, so I'm trying to find dsdt, or S prime. What would I do to my original equation? Okay, I'm trying to find dsdt, so we'll just differentiate implicitly with respect to t and just see what we get, right? If I differentiate implicitly with respect to t, on the left side I'm going to get S prime, right? On the right side, c is a constant, so we'll leave that out front. What's the derivative of capital R squared with respect to t by the chain rule?
2R.
2R.
R.
2R R prime minus the derivative of little r squared with respect to t?
2 little r, little r.
Hold on, is little r changing? Read the question carefully, right? It
At
says
a constant distance.
at a constant distance r,
So it's still minimal.
right? So the derivative of a constant is
The same.
0, right? Derivative of a constant is 0. So because this is constant distance r, we're getting a minus 0 there, right? We wouldn't write it, but I'm just putting it, purple goes with purple, right? So you can see why it's that way. And so already got S prime. Solve for S prime then. S prime is equal to 2C R prime, and all that is stuff that I'm given, right? C is some constant that they give us, right? R is the radius of the artery, and so we're taking this at the moment where the radius is that, right? So it looks like 1.2 centimeters, or actually 0.12 centimeters. Boy, that's small. Yeah, yeah, it is small. It's a small one. And drdt is 10 to the negative 5. So it's not changing very fast. But if we plug all that stuff in, what do we get? Somebody's got a calculator. What's that give us if we plug all that in? So 2 times 1.76 times 10 to the 5 times 1.2 times 10 to the negative 2 times 10 to the negative 5.
I got 0.055.
0.588.
5.
Oh, 558. Okay, and that would be, oh, I think that's good. That sounds good. Centimeters per second. So not very much, but it's a pretty small artery, right? So maybe, I don't know, maybe that is significant. That's how fast the speed is changing. So in other words, that's kind of the acceleration of the blood, isn't it? And it would be in, okay, but it's in centimeters per second, isn't it? Because the S is measured in centimeters per second. Doesn't it say that somewhere?
Very bottom. Very bottom.
Bottom.
Very bottom.
Very bottom.
Of your writing.
Down.
Right.
Down.
Very bottom of the screen.
Down.
Oh, way down here?
Yeah.
Oh, yeah, there we go, yeah. Okay, oh, and yeah, here, S is measured in centimeters per second, so then that would have to be centimeters per second, centimeters per second squared. So it is an acceleration. Okay? Make sense? Okay? All right. I will put up a little assignment for you.
Oh. It's not the right answer. It's fine. I think it's fine.
All right.